Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we were talking about simple harmonic motion. We said simple harmonic motion, it is a vibration of an object where the restoring force is directly proportional to the displacement of the object from the equilibrium. And we also said that there are three conditions for the motion of an object to be called simple harmonic motion. The first one, the restoring force must be directly proportional to the displacement. The second one, we said the vibration or the motion must be about the equilibrium. The third one, we said the motion must be on a straight line. Don't forget. Okay, and then today, we also talked about Hooke's law as well. We said Hooke's law states that or showed that the restoring force it is directly proportional to the displacement. And we had Hooke's law or Hooke's equation as well, which says the restoring force F elastic it is equal to negative kx. The force it is a vector quantity. It is measured in Newton. K it is a spring constant. It is a scalar quantity. It measures the stiffness of a spring, and then displacement it is also a vector quantity, can be positive or negative. It is measured in meter. Okay, and then we ended up right at this point here, but before that, of course, that is the equation actually, which we said F elastic it is equal to negative kx, and we said this negative stands for, or it represents that the direction of the restoring force it is inversely, the direction of the restoring force that is always opposite to the displacement of the mass, or direction of the displacement of the mass. Now, this regarding this study tip, I need you to disregard this one here. And the reason why, because this one actually works for all the questions that we have in this book. Perfectly fine. But the only problem is this is non-scientific, or you can say it is not science-based. What do I mean by this? That means it doesn't have any scientific base for this one. But I'll tell you something better than that, of course, so you can replace that study tip with. So let me give you a brief information regarding this one here. Consider we have a spring here, or at any case, if this spring it is vibrating or moving back and forth on a horizontal surface. Let's say this is the equilibrium position where displacement is 0. If we pull the mass to, let's say, a certain displacement here, you can see that this is a positive displacement because it is to the right. In order for you to do this, you need a force. We've previously mentioned in the other lesson here. So this force, you can call it what? You can call it applied force here. What is it called? Applied force in here. And then on the other hand, there would be a restoring force on this one, or there will be an elastic force. We could have, of course, draw this one here, this applied force. We could have drawn the arrow here. So it is going to be exactly this point here, starting from equilibrium all the way to this end. So that is the applied force in here. But on the other hand, there is a spring force which acts on the mass, always tries to bring it back to the equilibrium position here. So this, you can call it F elastic, which is trying to bring the mass back to the equilibrium here. This is, you can call it the force that is provided by the spring here. So one thing you need to know that is this F elastic, you can see that they're always equal in magnitude and opposite in the direction to the applied force. So this is, you can write this as a note for yourself, and it works for every single question, and is also science-based as well. So we can say F elastic, it is always equal in magnitude to the applied force, but opposite in direction. When we say opposite in direction, so we'll draw this negative here. So the only thing now you need to draw, or you need to write, is this equation right here. F elastic, it is always equal to in magnitude to the applied force, but in opposite direction. So this negative means that these are opposite direction. In other words, we can say that if you apply 100 Newton, let's just say, 100 Newton to the right, which is positive, correct? If it is to the right, 100 Newton, then the elastic force that is provided by the spring will also be 100 Newton, but this time it is going to be to the left. So you can see that these are equal in magnitude, but opposite in direction. Now, another case, what if you compress the spring here? So another example, so what if you compress the spring? So let's say this is the equilibrium, and then you use, or you apply a force. The applied force this time, it is negative 100 Newton. Why? Because now it is moving to the left or you can say the displacement to the left, it is negative. So there will be a restoring force here. This restoring force, it is going to be what? Guess what? It is going to be 100 Newton, but positive. So it is always equal in magnitude, but opposite in the direction to the applied force. What exactly do you mean by the applied force here? But this applied force can mean different things here. For example, this force that you use to whether stretch or compress the spring here. So we can say this applied force could mean the force that you use to stretch the spring. Stretch. Let's just write nicer. Stretch the spring. Or it could be the force that you use to compress the spring. Or it could also be force of gravity, by the way. Gravitational force can also stretch the spring, but how? I'll tell you how in a second. So we can say gravitational force as well. You can just call it Fg. So for example, bear with me. So we have a spring. We said this is the equilibrium position. So if you apply a force, in this case, this force here that extends the spring, you can call it stretch force. You could just write ST for short here. Then there will be elastic force in opposite direction. So these are equal in magnitude, but opposite in direction. By the way, this is going to be positive, but this one is going to be negative here. What about the compressed? The force that we apply could also represent the compressed force. What do you mean by compressed force? So imagine this is the equilibrium here, and here's the mass. So I apply a force in this direction, but this time to compress the spring here. So the displacement is negative in this direction. So the compressed or the force that I used to compress the spring is now going to be negative. Let's just say this is negative 100 Newton too. Now elastic force is going to be equal in magnitude but opposite. So elastic force is going to be positive 100 Newton there. So this is a compressed force here. What about gravitational force? Consider this. We have a pendulum is hanged vertically. So gravitational force tries to pull the spring downward, correct? So if it is going to pull the spring downward, we can say, elastic force is going to be opposite to this. So if we consider this one here, we can say elastic force that is equal to negative Fg here. So if we assume that this is Fg, okay, elastic force is going to be upward in this case, so it is equal to the gravitational force, but in opposite direction there. So these are, you can say the summary of all this, you can tell by knowing this one. It will always work, and that is science-based as well, which is perfectly fine, is better than the other one. I used to use the other one, but I believe it is best to use this one, so I would recommend you disregard that note and start writing this one or work on this one right here. There's one thing you have to be careful with this point here regarding the displacement, Baba. The question must tell you which way it is displaced so that we can tell whether if it is positive or negative. We know that if it is, if the mass is displaced to the right, that is positive. If it is displaced to the left, that is negative. But one thing that you can always be certain with, if we have a mass that is hanged with a spring here, this mass that is pulled by the gravitational force, so this displacement that is pulled by the mass, it is always considered negative. And that is, where do we get this one from? From the number line. We know that if it is to the right, positive, to the left, negative, and if it is downward, it is also negative, but we call it just negative x in this case, and if it is upward, we call it positive. So just remember this, whenever the question is asking about the displacement, Basha, then if the displacement is downward, it is going to be negative. So if you do calculations, you might get, even if you get a positive x, okay, because the negatives cancel out sometimes, just remember this, if you get a positive x or displacement, that is the displacement by the elastic force. Don't forget, not by the mass. But at that point, just remember the displacement by the mass is downward, so you can always make it negative. So whatever the answer you get as a positive, the displacement by the mass is going to be the same amount, but negative or downward there. Okay, so now let's use this, what we have just learned in calculation, see how it is. So remember, the only thing you need to know is this much right here. Okay, so now let's, and of course that one too here, there. Let's see how we can use or apply this in calculations. And of course you can, based on this, we can edit or modify some of the answers there as well. Not the answers, some of the signs, let's say. Okay, so let's bring the whiteboard here and do some calculations. Right. So that is one thing that we have. Let's see what it says and what do we have. It says, if a mass of 0.55 kilogram attached to a vertical spring. So what do we have now? We have a vertical spring. So here's a spring. A mass is attached to this spring here. This mass is 0.55 kilogram. So the mass is 0.55 kilogram. Vertical spring stretches the spring 2 centimeter. Don't forget, that means X, it is 2 centimeter. Okay, and if you want to convert this to meter, that is going to be 0.02 meter. Okay, the next thing it says from its original equilibrium position here. So that is the original, let's say that was the length of the spring, and then after that you attach the mass to this, which makes it or stretch it this much downward here. Okay, the question says, what is the spring constant? And remember this, we've mentioned that earlier, spring constant cannot be negative or 0, so make sure that you get a positive number at the end here. Okay, so the question says, what is what? What is spring constant? That is unknown. First of all, we have two things here. What force is pulling this mass downward? We've learned that this is what? It is called gravitational force, right? So let's just call it F2. Okay, but what force stops the gravitational force from pulling the mass forever, or stops the mass from going further down? That is elastic force, which is by the spring. And we said, based on the equation that we've learned, we said elastic force, it is always equal to the force that is applied, which is the gravitational force pulls the spring down, always equal in magnitude but opposite in direction. Don't forget this negative. But you also have to be very careful with this. Now you have to write the equation for elastic force. What is the equation of elastic force? It is negative kx. So don't say I've wrote a negative here, now why do I have to write it? No, because this would be the equation of the elastic force, and then now minus Fg, it is equal to mg, correct? Now, can I cancel out these two negatives? Yes. So we can say K, that is spring constant, it is equal to mg over the displacement here. Okay, so mg, the mass is 0.55 times 9.81 divided by the displacement, which is, we said 0.02 meter. Now, do the math, of course, you'll find the spring constant. Okay, so what is the spring constant? Let's just take a look at the number. It is 270 Newton meter. You can see that I got a positive number for K because it is a constant. It cannot be negative or 0. That is how easy it is, and it is science based on 2 as well, so you don't have to worry about this one here. Okay, now let's go to another question here. Okay, now practice the first question. We have a slingshot. It says a slingshot consists of a light leather cup. Okay, so there is a light leather cup. Let's just zoom in this one, make it bigger. Of a light leather cup, that is what it is. And I believe you do know what is a slingshot. Okay, so this one is right here is a slingshot. 2 elastic bands and a leather cup, you could say. Attached between the 2 rubber bands. We have 2 rubber bands, by the way. If it takes a force of 32 Newton to stretch the band, watch this. So this F, this is how much force it is required to stretch. Let's say this is the cup, and this is perhaps. Okay, these are the rubber bands, and this is the leather cup. How much force does it take to stretch? So how much force does it take? I should have drawn the other side so that we get a positive value, by the way. It doesn't matter here. Okay, so this is the leather cup here. How much force? So this is a leather cup, by the way. This is, we can say how much force this is how much force it is used to stretch. So can I call this one applied force or stretch force? Doesn't matter. What is this force? 32 Newton. So we can write applied force or stretch force is equal to 32 Newton here. Okay. The next thing says to stretch the band 1.2 centimeter. So we can say displacement is 1.2 centimeter. And if I convert this one to meter, it is going to be 0.012 meter. The question says, what is the equivalent spring constant? So what is spring constant? And that's it. So once again, we said the equation that we need to use, F elastic, it is equal to negative F applied, correct? Very, very good. So now once again, F elastic, it is equal to negative Kx, and then applied force. How much force is applied, by the way? Just 32 Newton. Once again, negative, negative cancel out. And then we can say K, that is spring constant, it is equal to 32 divided by the X, which is the displacement. I think I rushed a little, but that's okay. 32 divided the displacement is 0.012. The answer is going to be about, let's say, 2,666.6, but of course the book rounds this one to two significant figure, which is rounds up to 20, or you can say 2,700 Newton, and that is, if you convert this one to scientific notation, it becomes 2.7 times 10 to the power 3. That is going to be Newton per meter. This is the spring constant for this question too. Once again, if you use this equation, of course, it is sign-based, and then you don't have to worry about anything else. Okay, the next thing that we have, let's see what is next that we have. Okay, let's just go to another page. The next question says, how much force is required to pull the leather cup in question 1 to a distance of 3 centimeter from its equilibrium position here? Okay. Let me not forget, actually, perhaps maybe just give it a little bit of info there. The reason why I wrote this equation here, F elastic, it is equal to negative F applied, because if you're applying a force of 32 Newton in this direction, that is the force you apply, okay, then the elastic force is going to be 32 in the opposite direction. This is why we wrote negative 32, because F elastic is going to be the same amount, same magnitude, but in opposite direction. Okay. Now going back to the to this question, says how much force is required to pull. Actually, I forgot to mention one idea regarding this question. What if this question came in Uzari, but instead of having two leather cup or rubber bands, let's say, what if the question says find the spring constant or the equivalent spring constant for one rubber band? What would you do? In that case, whatever the answer you find, you will just divide by 2. Okay? What if we had 4 rubber bands and then the question is asking for 1, the equivalent spring constant for 1, then you could just divide by 4, or the final answer, divide by 4. You could divide the force by 4 first. If not, you could just, whatever the answer you get, you divide by 4 and that's it. So be aware of that one too, just in case. Because we have a similar question to that. Yes, that is for chapter 3, if you remember. Actually, no, it's a bit early, I guess, to that. Okay, right, question 2. What does question 2 say? It says, how much force is required to pull the leather cup here? So how much force is required to pull the leather cup? Isn't that the applied force? The question says, how much force or how much applied force is required? So this is the one that you need to do. To pull the leather cup of question 1 to a distance of, so we have displacement, which is 3 centimeter, 3.0 centimeter, or you could just say 0.03 meter. Always use meter, convert. Okay, that is this from the equilibrium position. But of course, if you want to find this one, you must have spring constant as well. But we already found it in the previous question, which was 2.7 times 10 to the power 3 Newton per meter, because it says in the previous question. So the same, it's the same rubber band, so same spring constant or equivalent spring constant. So how do you do that? Once again, just use the same equation that we said. We said F elastic, it is equal to what? It is equal to negative applied force here. What force is this at this point here? It is the force that you apply, or you can say the force that you use to pull the leather cup, which is the same thing there. But don't forget, F elastic, by the way, whatever whatever, in this case, you can find F elastic. Whatever F elastic, it is going to be equally magnitude opposite to the applied force. But if you use this equation, you don't have to worry about anything else. So once again, F elastic, it is equal to negative kx, and that is equal to negative applied, yes, because these are equal in magnitude and opposite in direction. Once again, these two will cancel out. Okay, so and then F applied, we can say it is spring constant times the displacement. Doesn't matter which side you write them actually, because for some reason now the unknown just is at the other side. So that is 2.7 times 10 to the power 3 times the displacement, which is 0.03. That is equal to the applied force in here. All right, so let's just find this one here. What is it equal to? You could do the math, use a calculator, but I have something an easier way, which is 81, right? So we can say applied force now, it is 81 Newton, and that's it. Right? So just use this equation, and that's the whole thing. You don't have to worry about anything. All right. That's it. All right. Moving to something else. The next thing that we have says a stretch or compressed spring has elastic potential energy. Now let's go back to this one here, or perhaps you can think of this one. It says, consider an archer shooting an arrow from a bow, bending the bow by pulling back the bowstring. That, of course, is analogous to stretching a spring here. So let's talk about the spring one more time here. We have a mass spring. This spring, here's the equilibrium position, let's say. Okay, if you pull the mass to this side here, of course you need a force to do that. We said we call that force applied force here. Then there is elastic force as well, correct? Which is acting on the opposite side, trying to bring the mass back to the equilibrium. But once you stretch the force and hold the mass there, because the spring is stretched, now this spring, of course, stores a type of energy. It is called elastic potential energy here. How do we know it stores elastic potential energy? We know because if you just let go of the mass, what do you think will happen? Now the mass is going to start moving back and forth. Will it start moving back and forth if there is no energy on the spring? The answer is no. Consider, for example, this mass. What if it was at equilibrium? If you let it go, will it ever stop moving back and forth? The answer is no. But if you pull it back, because you have to do some work in order to do that, that work, of course, or the energy you do will be stored. The energy that you use to pull the mass spring will be stored, transferred into the spring. Now this energy is stored as elastic potential energy, and we know that, like I said, if we let it go, it is going to swing back and forth. That's first. What if we have? What about when an archer is bending a bow here? Consider that is we can say it is the same thing. So here's what a shape. Okay. That's not a very good diagram, but this is a string, a bow. So the whole thing is a bowstring. Now, so at this point here, there's no energy in the system. This is elastic. This bow can bend as well. So what happens when you, let me see if I can draw all this at once here, because that'll be better in order to move the thing there later. Okay. Perfect. Okay, so what happens, the reason why I did this so that we can all move this all together. What happens when we, let's say, stretch or pull the arrow backward using actually holding the arrow to using or pulling the string backward? Okay, so here's the string here, but once you're doing this, let's see if we can remove this one too. Let's just move this one here. Maybe we'll need it soon. Okay. Now that is at this point here, this is the arrow on the string here. So the string is pulled backward. Okay, that string, of course, it can pull the bow too. So now we can see that if the arrow is held at this point, it is not moving or it's not let go. So this, because you're doing some work in order to pull the string, so there is energy inside the system here. But what is the energy of the system? It is elastic potential energy here. The system, or the energy of the system now, it is elastic potential energy because this energy is stored in the system, no part of the system is moving. But what happens when you let go of the arrow? Once you let go of the arrow now, the arrow it is going to move in the air now. So the arrow is in the air. If the arrow is moving, what type of energy is in the arrow? That is kinetic energy here. But what do you think will happen to the string? What do you think will happen to the string and the bow at this point here? Just think we could just erase this one now. So now this string will go back to its shape here. But remember, this string keeps vibrating here, or it is still moving, right? Once you let go of the arrow here. So the string moves a little, the bow is moving a little. But if I want to take a percentage, I can say 99% of the energy of the bowstring now, it is converted into the arrow, which is now, it is kinetic energy. But this percentage, or this percent that is left, it is going to become kinetic energy inside the string and the bow, because they will be moving a little first and then vibrating. So that'll be the remaining, or the 1% of the energy that is left, assuming no energy is lost, by the way, correct? But once this one stops vibrating or moving, that energy clearly at this point has to go into the air so that this one stops. Then the energy would only be left in the arrow, which is in the air here. So what do we learn at this point? We can say, or consider this, or say this is analogous to the spring here. Once you stretch, it is the same as you stretch the spring, has elastic potential energy. But once you let it go now, it has this elastic converts to kinetic energy. It's the same as when you let go of the mass, now it is going to move back and forth or at equilibrium. All this elastic have converted to kinetic energy. But another difference from a spring system, it keeps moving back and forth, or the energy converts between elastic and kinetic. But here we don't have this because the arrow doesn't go backward or go back into the bowstring there. So once again, it says once the bowstring has been pulled back, the bow stores elastic potential energy and all that. When the bowstring is released, most of the bow's elastic potential energy is converted to kinetic energy of the arrow. The rest, or the remaining elastic potential energy, is converted into the kinetic energy of the bow and the bowstring here. But if we says the mechanical energy of the bow and the arrow system is solely kinetic, once the arrow is in the air, and then the bowstring is or stops moving there. Okay, because mechanical, actually, no, I mean, even if it is not, for example, even when the bowstring or the arrow is still moving, we can say the entire energy of the system is kinetic because now there's no elastic anymore. So because mechanical energy must be converted, we can say the total kinetic energy of the bow, the arrow, and the bowstring must be equal to the elastic potential energy originally stored in the bow. All right, now let's talk about something else, and that is the simple pendulum. Okay, what is a simple pendulum? I should have brought an object here. So a simple pendulum, it is a mass attached to a string. That mass can oscillate, can move back and forth. Imagine maybe for next time, perhaps. Okay, so once again, we have a mass attached to a string here. Could be a rope or whatever. That's why we call it simple, because it has a simple or has a mass on the string which is attached to something. Then it moves back and forth, oscillate back and forth. Okay, that is called simple pendulum. The name of that mass, it is called bob in physics, by the way. So simple pendulum, it is a mass on a string or a rod that swings back and forth under the gravity's influence, we can say, showing a periodic motion. There's one thing you need to know, which is very, very important at this point. Let me show you this. First of all, let's draw a simple pendulum. Here's what we have, and here's a string, and we can say this is a mass. Okay, right at the center. Once again, so this mass, it is called bob, and this is a string here. And this is, you can use a rod too here. So this mass, it is swinging back and forth here. So at some point it is here, it is going moving or back and forth here. This motion, it shows periodic motion. Do you remember what was periodic motion? We said it is the motion of an object that repeats itself over or at regular time intervals. That is because it moves back and forth, so we can call this one periodic motion. But there is one thing you need to know at this point. When we were talking about the mass spring system, when we were stretching the spring or pulling the mass to one side, what force was trying to bring the mass back to the equilibrium? It was elastic force, right? And this is the applied force, and to this side, elastic force was trying to bring the mass back to the equilibrium. But what force is bringing this mass back to the equilibrium once it is oscillating here? We'll say it is the gravitational force. In order to be more specific, it is a component of gravitational force. Let me tell you more about what I mean here. So once again, if this is the pendulum here, first of all, if this pendulum is not swinging, we know that gravitational force acts on the pendulum, which is downward. But what stops the mass from going downward? That is F tangent, which is in the string. That is when this mass is not oscillating. But what about when it is oscillating? So here's the mass that is oscillating. At one point, it is at this point here. So this mass keeps oscillating back and forth, correct? By the way, if it is not oscillating, the point where it is at rest, you can call it equilibrium. So equilibrium for a pendulum here, it is at this point here. We can call this one equilibrium, where the displacement is 0 at this point. Okay, the next thing that we need to know is this. Now, do you remember we said we have gravitational force, and so there's F tangent upward. Don't forget the two. These are equal in magnitude and opposite in direction. So we can say Fg, it is equal in magnitude and opposite to the F tangent. Equal in magnitude but opposite in direction. What about at this point here? We know that gravitational force still acting on the pendulum. Gravitational force, it is always directly downward. But as you can see here, once this pendulum is swinging back and forth, it is traveling a certain displacement here. This displacement, or you can say there is a certain angle here. This angle, you can call it the amplitude in a pendulum here. And then, so let me erase this one. X is 0. So at this point here, this is still gravitational force. But now, because this gravitational force is at some angle, it will analyze, or it will be divided into two components. What are these two components? One of them, it is going to be on the same line as, because don't forget F tangent is still upward, right? One of them, it is going to be in the same line as the tangent force, because these two must still be equal in magnitude and cancel out. And then the other one is going to be right at this point here. Okay, but we do know that, by the way, these two angles will always be the same. I think it is called corresponding angle in math. And we do know this one by knowing this one, let's say. If this angle is 30, what is this angle? That is also 30, we can say, correct? So these two are exactly the same thing. So these two angles will always be the same to one another. And we've learned that whichever the side that is with the angle, that would be cosine, the other side will be sine. So this Fg now, it becomes, not this one here, okay. Make this one, okay. So this point here, this side would be Fg cosine theta, and then the other side is going to be Fg sine theta. Once again, this is F tangent. Once again, F tangent, these are still, one of them, F tangent is upward, Fg cosine theta is downward. So these two are still equal in magnitude but opposite in direction. So F tangent, it is equal to Fg cosine theta. So these two cancels out. Well, Bash, if these two are canceling out, so which one of these components, or what exactly brings this mass back to the equilibrium? Do you see this force, Baba? This force, it is pointing towards the equilibrium, correct? So now the restoring force in a pendulum, we can say it is Fg sine theta. Now, once again, the restoring force the restoring force in a pendulum, it is equal to Fg sine theta. You can call it is a component of gravitational force. We can also sometimes, because this has been in Uzari, you can say a few times, okay? One of these components, watch the path of the pendulum. Now, this component, if I erase this one because we no longer need this, because we've already analyzed this to two components, x and y, correct? Yes. So now I have two components. One of them, it is perpendicular to the path of a pendulum, which is Fg cosine theta, right? And then the other one, you can see that it is tangent to the pendulum's path, or circular path, correct? So now, which one of these is the restoring force in a pendulum? The one that is perpendicular to the pendulum's path, or the one that is tangent to the pendulum's path? We'll say it is the one that is tangent to the pendulum's path. Basha? This Fg sine theta, it is tangent to the pendulum's path. To the pendulum's path. Because in Uzari, they'll tell you which one of these two is the restoring force. So it is a component of gravitational force, Fg sine theta, which is tangent to the pendulum circular path. And we do know that if you're given the mass, Fg, that would equal to what? It is equal to mg. So don't be surprised if you see mg sine theta, because that'll be the same thing there. Okay, so this is the restoring force in a pendulum. Once again, in mass spring system, the restoring force was elastic force. So perhaps let me remind you this one as well. For mass spring system, the restoring force was elastic force, and it was equal to negative kx. But now for a pendulum here, that is for mass spring system, but for a pendulum, it is a component of gravitational force, which is called Fg sine theta. Or you can say the component of the gravitational force that is tangent to the pendulum's path. And by the way, we've had something similar to this in the torque, if you remember, because this one is, we can see that this one is tangent to the pendulum's path. If they gave you the length of the string here, this would be the force that causes the rotation of the pendulum. So you can find the torque by using this too, because this component will be perpendicular to that part, don't forget. But because we're talking about the restoring force here, this part, it is equal to an opposite to the F tangent, so these two cancel out. The only force that is bringing this mass back to the equilibrium is Fg sine theta, which is tangent to the pendulum's path. Do not mix with the other one there. Okay, that is all regarding to the pendulum's path. By the way, don't be surprised if they at any point here, they ask you for the F tangent. They might say find F tangent of in the pendulum, or find F tangent of the string in the pendulum here. So if they ever do, that is something different here, because we said if it is not oscillating, these two are equal in magnitude and opposite in direction. But now since we have an angle, but these two are still on the same line, so we can say F tangent, it is equal to Fg cosine theta. If they ever ask for F tangent, you can find or use Fg cosine theta to find F tangent in the string or inside the pendulum string there. Okay, that is all regarding to the restoring force in a simple pendulum. So once again, in a simple pendulum, we assume the mass of the bob is concentrated at the center. That is obvious, just like to make calculations easier. And the mass of the string is negligible because we say it's a light string there. The effect of friction and air resistance is disregarded because friction and air resistance try to slow the motion down, and that is something we don't want, so we ignore the effect of these forces. In physical pendulum, we mean, for example, like when the system is not ideal, of course, air resistance and friction would affect the motion of a pendulum and they slow the motion down. So we can say we will take their effect into consideration. Once again, the restoring force in a pendulum is a component of the bob's weight. Don't forget, when we say the bob's weight, we mean Fg, don't forget, okay? The bob's weight, that is Fg. It is a component of that Fg. The two forces acting on a pendulum bob, we said, it is the tension on the weight, that is when it is not oscillating here, or not swinging. We said F tension, it is upward. You can write this and then Fg is downward here. These are the two forces, but once it is swinging, then this one would analyze or would be analyzed into two components. We can say Fgy and Fgx here. What do I mean exactly by Fgy and Fgx? And here, if I walk you through this one, or if we take a look at this diagram here, this is the vertical component. You can call it Fy here. So this one becomes x at this point here. By the way, this is a little bit after a little bit of rotation, but you do know that you can always, for example, if you rotate this one a little, so this side is still x-axis, this side would be y-axis. So which component, which part would bring the mass back to the equilibrium? That is this Fg, that is equal to mg sine theta. Okay, there's, yes, so we have Fg, x, mg sine theta, which brings the bar back to the equilibrium position. So mg sine theta is called the restoring force in pendulums. The next thing, this note, we've already mentioned that. Note that the restoring, actually, I have to mention this one too again. We said if the pendulum is not swinging, or you can say at equilibrium position, what is the angle at equilibrium position? 0, right? So in this case, we can say the restoring force is 0 because we said Fg sine theta, correct? That is the restoring force for a pendulum. If the angle is 0, so the restoring force at equilibrium is also, we can say the restoring force is 0 at equilibrium. In this case, we will have F tangent and Fg only, these two, without any restoring forces at the equilibrium. Okay, one more thing here says, what does the restoring force on a pendulum depends on? You have to be really careful at this point. So the restoring force in a pendulum here, it is equal to, let's just call it restoring force. You can write this one too. Restoring force, it is equal to, we said Fg, which is equal to mg sine theta, correct? So we can say it depends on the mass, which is directly proportional. It depends on the angle sine theta, that is also directly proportional as long as it is between 0 to 90. And then you can add one more thing, by the way. Now, when we talk about pendulums, all the situations or cases we have, it is on the Earth. But if we change the plate, which is gravitational acceleration on Earth is constant, but by any chance, if we take this pendulum to another place, that is g is not 9.81, then that g, of course, that affect the restoring force too. So you can add third one here, Fg, or the gravitational acceleration. Sorry, not Fg. You can say g, which is, we can say free fall acceleration. Free fall acceleration, or gravitational acceleration. Free fall acceleration. Okay, that would be g there. You can add this one to that because now these are complete. That would be the mass. These are directly proportional gravitational acceleration or free fall acceleration, and then the angle theta. Okay, or the angle of the displacement. All right, for small angles, the pendulum's motion is simple harmonic motion. Now, previously we talked about this one, but I'll just remind you here again. Now, we've mentioned the condition for something to be called simple harmonic motion. Okay, so for simple harmonic motion, we said there are three conditions. Restoring force must be directly proportional to the displacement, that is first. And then second, we said the motion must be at equilibrium. Third, the motion must be on a straight line. So if we have, or if we go back to pendulum here, so here's a mass, or let's say this is the mass. This is the equilibrium position. It is going to swing back and forth. Now, the further the mass goes, of course, the bigger the angle, yes or no? And if you have the restoring force, what is the restoring force it is equal to? You could just call it restoring force. It is equal to Fg sine theta, correct? So now, the further the mass is moving away from this is equilibrium, you can say. You can say displacement is 0. Now, the further away the mass is going, or the further the mass is going away from equilibrium, the bigger the angle. Ebasha, if the angle is bigger, isn't the restoring force gets bigger too, because that would be mg sine theta, correct? Now, there is a direct relationship between the restoring force and the angle theta right here. So we can say the larger the displacement, you can call this one displacement here, The larger the displacement, the larger the angle, which makes the restoring force to be larger too. So these are directly proportional here. The larger the angle, the larger the restoring force. And that is the first condition to consider the motion of a pendulum a simple harmonic motion. What was the second condition? It must be moving back and forth about equilibrium, which it does. But then the third condition, if the pendulum is moving with this wide, let's say, circumference, then of course this motion is not in a straight line. So can I call this one simple harmonic motion? The answer is no. Previously we've mentioned that in order to call the motion of a pendulum a simple harmonic motion, this angle that it makes, it has to be, let's say here's the pendulum, right? This angle has to be really small for this to be in a straight, or for this motion to be in a straight line here. So in order for this circumference to be a straight line, this angle really has to be small in this case. And in order for this to be small, then this pendulum cannot swing anything more than this, let's say. That is one side, and this is the other side. So this is how large the angle is for this pendulum to swing back and forth. Why? Because if you want this pendulum to move in a straight line so that we can call this simple harmonic motion, then this angle that the pendulum is swinging with must be less than 15 degrees. It cannot be even equal to 15 degrees. So if this angle is bigger or equal to 15 degrees, then it is not simple harmonic motion, okay? It is not simple harmonic motion. It is only simple harmonic motion when it is smaller than simple harmonic motion when it is smaller than 15 degrees. Then we can say the motion of this pendulum is considered as simple harmonic motion. Okay. All right, so under what condition is a pendulum's motion considered a simple harmonic motion? Remember, we said when the angular displacement theta, it is less than 15 degrees. You have to keep that in mind. In a mass spring system, the restoring force in a simple pendulum is not constant, and that is obvious too, because previously, because once a pendulum is oscillating, so this angle is changing as well, correct? As long as the angle is changing, the restoring force is not constant as well. You can say restoring force, it is equal to Fg or mg sine theta. This angle is changing, increasing or decreasing as it swings back and forth. So because the angle is changing, that means the restoring force is also changing. So it is not constant. It is maximum at maximum displacement, and it is zero at equilibrium, we can say. So when the maximum angle of displacement theta is relatively small, less than 15 degrees, and sine theta is approximately equal to theta in radian, the pendulum's motion is an excellent approximation of simple harmonic motion, which we have just mentioned. Okay, gravitational potential increases as the pendulum's displacement increases. That is also another interesting fact regarding the pendulums here. So we said at this point we're considering two types of potential energy actually. So potential energy can be two types. Can be elastic potential energy, or it can be gravitational potential energy. Gravitational. For elastic, of course, we've said that it is equal to 1/2 kx squared, but that is not an equation you have to worry about because we don't have it this year. But for potential, it is mgh. So gravitational potential energy depends on the height, and you need to know this one. Okay, so what exactly this has to do with the angle theta here? Now here's a pendulum swinging back and forth. We know that if the pendulum is here, here's, let's say, and just go back to this. I just call it, here's the mass. As this pendulum, it is swinging, it is moving away more and more from the equilibrium position. That is for both sides, yes or no? But as it is moving away, you can see that this height is increasing, correct? Dash of the height is increasing. So what do you think will happen to the, let's just say we have a pendulum, we just pull the mass back more and more. The larger the larger the height, or the more that you pull the mass backward or in one of the direction, the larger the height of the mass or the bob will be. If that is the case, then we can say gravitational potential energy increases as the mass goes higher and higher. So, and I can remind you this as well. So as the mass goes higher and higher, there is an energy inside a pendulum. That energy is called gravitational potential energy. G for gravitational potential, which equals to mgh. So the bigger the height, the more the energy that is stored inside a pendulum here. For elastic springs or mass spring system, what was the energy that was stored inside the system once it was stretched? We said that energy was elastic potential energy. It was elastic, okay, which was once again negative, 1 over 2k x squared. So remember, for mass spring system, the energy is elastic, but for a pendulum, it is gravitational potential energy. Why? Because if we assume that, again, if we assume this is zero height, then the further it goes higher and higher, or as it moves away from the equilibrium position, as the distance increases, you can see that the height increases, which means the gravitational potential energy will increase. By the way, when the mass is at maximum displacement, the energy of the system, you just, for example, hold it here at this point, the energy of the system is now going to be solely or only gravitational potential energy. But what happens when you let it go? That gravitational potential energy, it is going to convert to kinetic energy, all of it at the equilibrium position. All right. What else do we have? So you can see the mechanical energy of a simple pendulum is conserved if we assume that the situation or the case is ideal, which means no friction, no air resistance. That is first of all. Second, it says, however, the spring's potential energy, if we go back to the spring that was elastic, but now for a pendulum, it is gravitational potential energy. And then we define gravitational potential energy, let's say to be 0 when it is at lowest or at equilibrium. Then point number 4, gravitational potential energy is maximum when the mass is at maximum displacement. All right, a few more questions for this session. It says, what type of energy of a pendulum bob before it is released? And how does this energy of a bob change as it swings through one full cycle? Now, before answering this question, I would like to tell you one thing, or perhaps let's draw something, a table similar to what we have done for a mass spring system. What do I mean by this? We have a pendulum here, and let's say this is the equilibrium position. At one point, the mass is at the maximum displacement. And it could be at the other side too here once it swings to the other side. Hopefully these are the same. Maybe not precisely, but okay, I guess. This mass is too big, I guess. Let's just make it smaller. So here's, I think we can, all right, that doesn't change or make any difference. All right, so this is equilibrium. This is how it is going to swing back and forth. This is how it is going to swing back and forth. This line is not a perfect symmetry, but I think it is sort of, all right. Maybe it is the drawing, not perfect. But still, this we can say this is point A, this is point B, you can say equilibrium, and this is point C as well. Do you remember what we've done before? So what are the factors that we're going to consider as well? But we know that there is angle theta too, don't forget. At this point, equilibrium, the displacement is 0. And at this point there, you can see that this is maximum, can I say this is maximum displacement from equilibrium? Yes. Okay, this is maximum. And then the other side is maximum too, but that'll be the other way around or the opposite direction here. So the first thing that we're going to consider is the displacement here. The displacement at this point, we can say it is maximum. Once again, instead of writing to this side, I'll write the other way so that we could do all this and you can see the effect. Perhaps maybe it will be more organized if we do this. All right, so displacement is maximum, because you can see that here, the further the mass, the more the displacement, so it is maximum. What about the force in here? The restoring force. restoring force. By the way, don't forget the restoring force in a pendulum here, it is mg sine theta, a component of the bob's weight, which is tangent to the path of a pendulum here. So if the displacement is maximum, you can see that because the angle is maximum there, so we can say the force is maximum. What about the acceleration? The acceleration is also maximum. What about the gravitational potential energy? This time it is not elastic, it is gravitational. Let's just write a little bit lower maybe. Gravitational potential energy here. So potential energy, but gravitational, that is equal to mgh, don't forget. The height is maximum. Gravitational potential energy will also be maximum. Now we have one more thing that which we didn't have in a mass spring system. That is the angle theta. At this point here, you pull the mass to the maximum displacement, so this angle is the largest at this point, so that is also maximum. Now, we're holding the mass, it is not moving, okay? You can say it is this point, so the velocity, it is 0. What about kinetic energy? Perhaps maybe we need to move this a little. What about the kinetic energy? Kinetic energy is also 0 because the mass is not moving. What about momentum, which is equal to mass times velocity? That is also 0. Now, what do you think will happen once we let go of the mass? It is going to swing back and forth. But what exactly would be these variables once it is right at this point, but it is not stopped, it keeps moving. It's just like the moment when it is right at this point here. So what do you think will happen to the displacement? The displacement now, it is going to become what? Going to become 0. If the displacement is 0, that means the angle is also 0. So what is the restoring force? Is 0. What about the acceleration? It is also 0. What about the gravitational potential energy? That is, again, we can say it is 0. What about the angle theta? That is 0. You could have wrote angle theta here with the displacement, but that is fine. But so you can see the pattern now. All these are those variables that were maximum, now they're 0. But what do you think will happen to the velocity now? The velocity, it is going to become what? It is going to become maximum. Why? Because now all that potential energy here, which is maximum, all of this is going to convert to kinetic energy here. That kinetic energy makes the mass to move with the fastest at the equilibrium here. What about kinetic energy? All right, what is it? Maximum. Well then, what about the momentum? That is also maximum. Of course, these are Benenuzade too. Now, what do you think will happen as the mass passes the equilibrium? Now it is moving towards point C. Now it gets to or reaches point C here. That is the point where it completely stopped. Now it is about to go back. So those variables that are 0 now, they're going to become what? Maximum. And those variables that are maximum, it is going to become 0, which is exactly the same as point A. So point C and point A, these two points are exactly the same. The only difference, this one is moving towards the equilibrium, it's moving away from the equilibrium, and that's it, or it is about to move back to the equilibrium. But that is not the whole thing. Don't forget, what if the question is saying a mass is released, it is at a point, it is, let's say, moving towards the equilibrium. What do you think will happen to the restoring force? It is getting smaller and smaller. So if it is moving towards the equilibrium, for those variables that are maximum, they're approaching 0. So they're going to decrease, right? Each one of these variables are decreasing because they're going to change from maximum to 0. What about those variables here, or those factors? These are going to increase because they're changing from 0 to maximum. So these are increasing. That is if it is moving towards the equilibrium. What if it is moving away from equilibrium? Then, of course, the opposite of this would happen because these are changing from 0 to maximum. So those are increasing, but these would be decreasing. And that is the whole thing regarding a pendulum. Don't forget this. Now, we can answer this question. It says, what type of energy of a pendulum bob before it is released? So before it is released, we said it was, or it is at this point, it has gravitational potential energy. That is before it is released. Second says, What is the energy of a bob? Of the bob change, or how does the energy of a bob change as it swings through one full cycle? Now you have to know this one as well. One full cycle. There is also, in order for this one to make one full cycle, this is what is going to happen here. So if we assume this is point A, has to go all the way to the other end, which is point B, and then has to come back to the same point, that is one full cycle. So this is, for example, if we start at one point here, let's just call it point A all the way to this point, A to B, that is half a cycle, and then B to A, that is the other half a cycle. So we can say half a cycle to go and then half a cycle to come back, which is the same as going from point A to point B, and then from point B to A again. That is one full cycle. Okay. All right, I think we're approaching the end of this session here. Okay, so once again, says what is the energy, or what type of energy of the pendulum before it is released? It is gravitational potential energy here. Solely, that means it is only gravitational potential energy. G stands for gravitational, by the way. So how does this energy change during one full cycle? We said it's maximum here. This gravitational potential all converts to kinetic at equilibrium. So can I say gravitational potential is minimum here? Yes, but what is maximum? Kinetic energy. What do you think will happen as it go all the way, for example, to the other end? Now this kinetic decreases until it becomes zero, but gravitational increases until it becomes maximum. Then the cycle repeats again. That's what happens. So at equilibrium, GP decreases to zero, because that, you can see that decreases more and more until it becomes zero. But kinetic energy, starting from this point, increases until it becomes maximum here. But what happens after it passes through the equilibrium? We said now the gravitational potential, if we start with that, increases more and more until it becomes maximum, because the height increases more and more. So maximum, but kinetic energy decreases because it slows down until it fully stops. So kinetic energy will be zero at maximum displacement. That is through half a cycle. The other half is just going to be exactly opposite, and then the cycle repeats. Last question for this session, it says, in a simple pendulum, the weight of a bob can be divided into two components, if you remember we said it. One component that is tangent to the bob's direction of the motion, and the other one is perpendicular to the bob's direction of motion. Which one of these is the restoring force? Let me draw this one real quick for you, and then you can decide which one is it. Here's a pendulum. We said this is FG. This one, and if we consider this is the bob's path, so one of them, it becomes, you can see that one of them is perpendicular to the path. The other one is tangent to the path. We said this one is FG cosine, because this would be the same angle there and there. This FG sine theta. Which one is the restoring force? So it is the component that is tangent to the bob's path. That is the restoring force, which is equal to mg sine theta, because it always brings the mass or the bob back to its equilibrium position. I've already talked about this one here, and this is the table that you need to know. You can go through this one too. Next time, inshallah, we'll start talking about energy conservation in a pendulum there. And then after that, we'll continue. Okay, that'll be the end of this session. Keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.